In this lesson, we're going to look at a technique of integration that's known as the method of substitution, which is really based on the chain rule. Before we get started, we're going to look at a review of differentials, which are crucial to what we do in this section. Differential is something that we get from a function related to the derivative. If you give me a function y equals f of x, the differential is defined as dy, which is thought of as a variable, which is the derivative of f times dx. In a way, it's a measurement, an approximation of how much y changes for every change in x, for a certain change in x based on the derivative. So really all you have to do is find the derivative of the function and then multiply by dx, or what it looks like multiplying by dx. So let's look at the very first example here. We're going to find the differential for sine of 3x. We first find the derivative of the sine of 3x, which is the cosine of 3x. And then the chain rule says we have to multiply by the derivative of the inside, which is 3. Now, because our function is a function called y, we call this dy, and it's equal to the derivative multiplied by dx. Some people like to think about it as if you say, well, let's find dy dx. So that means the derivative. That would be, as we already said, cosine of 3x multiplied by 3. And then if you multiply both sides by dx, or what it looks like multiplication, you get what's known as the differential. Okay, so for the next one, same sort of business. If I were thinking about the derivative, it would be dp dq. So what I'm looking for is dp. We're going to find the derivative of this quantity and then multiply that derivative by dq. So the derivative I know is actually going to be a rather complex thing, so I'm going to start a parenthesis. The reason that I know it's complex is because here I have q times the quantity 1 plus q cubed. Since it's q times that, we're going to use the product rule. We'll take the derivative of q, which is 1, and then we leave the 1 plus q cubed alone. And now we need to leave the q alone, and we take the derivative of 1 plus q cubed, which requires the chain rule. We will bring the 3 down, lower the power by 1 plus q, not cubed anymore, but squared, and then we multiply by the derivative of 1 plus q, which is just 1. Now that's the entire derivative that we just wrote in parentheses, and so we have a dq here at the back end. And finally, if u is equal to 16x squared plus 4x, again, I would think about the derivative as du dx. So we take du, and it'll be the derivative of 16x squared, which is 32x, plus the derivative of 4x, which is 4. We're going to multiply this entire right side by dx, and so it's going to look like that. We need those parentheses. Now I want to give you a little bit of a motivation for the method of substitution. Let's suppose I'm going to take the derivative of something like the square root of 1 plus x to the 4th. Well, when I do that, remember that the derivative of the square root using the square root is meaningless, so we instead write it as to the 1/2 power. And so we would get 1/2. And now we leave the inside stuff alone and lower the power by 1. So it would be negative 1/2. But on the inside, we write what we had before. The chain rule says we have to multiply by the derivative of the inside, which is 4x cubed. So what the chain rule is going to do for us, if I were to simplify this, I would get 2x cubed times 1 plus x to the 4th to the negative 1/2. What the method of substitution will do for us is it will allow us to find antiderivatives of things like 2x cubed times 1 plus x to the 4th to the negative 1/2 dx by recognizing that there is some sort of object here, the 1 plus x to the 4th, whose derivative or something like its derivative is lurking about. The derivative of 1 plus x to the 4th is 4x cubed. Well, I don't have 4x cubed, but I have a constant multiple of 4x cubed, which is this 2x cubed out there. So we're trying to reverse this process. Rather scary looking slide here, but here's how it works. If we have a differentiable function g, whose range is an interval I and f is continuous on I, then when I take the antiderivative or the integral of f of g of x times g prime, we just get f of u du. We're making a substitution here where we let g of x be u, and then g prime x dx is du. That's precisely the presence of that differential that we talked about earlier. So here's how we apply it. When we're given an integral, we want to find some sort of expression in the integrand whose derivative is also part of the integrand, up to a constant multiple. Okay, so remember in the previous slide, we saw the 2x cubed when really the derivative of the inside was 4x cubed. So it could be a constant multiple of the thing that we're looking at. Find the differential of that u thing, and then you replace the expressions in the integral with u, and then you'll multiply or divide your differential by a constant value k, so that k times g prime dx is part of the integrand. It's kind of hard to see right now, but you'll see as we do the examples. Then you want to rearrange the integrand to make this k g prime of x appear and replace it with k du, because du is g prime of x dx, so g prime of x dx becomes this du. Integrate both sides integrate the expression using just your elementary formulas, and in your answer you want to resubstitute. So let's ask this question. Why is it that I know that this particular integral can be evaluated using substitution, and then once we know that, we're going to evaluate the integral? So here's the reason for this. I look and I say, well, I've got the cosine of something other than just x. And if you remember, your formulas include, hey, there's this integral of the cosine of x dx. I know that's the sine of x plus a constant. Well, I've replaced this x by something kind of ugly, namely the 16x squared that's here. Okay, so I kind of draw my attention to the argument, that's the argument of the function. When I take the cosine of something, that something is called the argument of the function. And I look at that argument and say, hey, that is an expression whose derivative-ish is lurking about. If I take the derivative of 16x squared, I get 32x. Well, I don't have 32x, but I have a different multiple of x, and so that's the indication as to why we would be able to use substitution. So let's do our first substitution problem. I've already acknowledged that the 16x squared's derivative is lurking about, that 8x. So what I'll do is I will let u be equal to the thing whose derivative is lurking about, the 16x squared. I'm going to do the differential. So remember, the differential, you take the derivative of what we've let u be equal to, so that's going to be 32x, and the differential is du over here, and I forgot to write my x there. So 32x dx. And now what I want to do is I say, well, let's see, I've got 8x dx. I want 32x, or I have 32x dx over here. So in order to get rid of the 32, what I'm going to do is I'm going to multiply both sides of this equation by 1/4. And when I'm done, I'll get 1/4 of du is equal to 8x dx. So we're going to do a little bit of rearranging in this expression here. So I'm going to write this as the integral. I'm going to put this, changing color here, I'm going to make this the cosine, and the 16x squared I'm going to put in red, because that's what I said was equal to u. And then the 8x dx I'll have as blue, and I'm going to put that in a set of parentheses, 8x dx. Now over here, I have the 8x dx, which I'm going to replace by 1/4 du. So 1/4 du is over here. And then the 16x squared is going to be replaced by u. And now I have to put everything else in. So I have the integral of the cosine of u times 1/4 du. So the 1/4 we can bring out front. 1/4 integral of the cosine of u du, which is just one of our basic formulas. This is going to be 1/4 of the sine of u. Don't forget your constant. And then we resubstitute u equals 16x squared. So this u is going to become sine of 16x squared plus a constant. Okay, so we've seen one of these examples where we look for an expression like 16x squared whose derivative or a multiple of the derivative is sitting inside the integral. So take a moment on your own, maybe pause the video, and look at these 6 integrals. We've got 6 of them down here. 4 of them can be evaluated using substitution. So we're going to figure out which 4 they are, and then we're going to evaluate those 4. Okay, so did you figure out which ones were the ones that require substitution? Some are, I think, a little bit easier to see than others. For instance, this one down here in the bottom left corner, I think it's pretty easy to see because when you take the derivative of 6y to the 4th, you'll get 24y cubed. Well, I have 2y cubed, close enough. Okay, so we could do something to the 24y cubed to get the 2y cubed. So this one will be one of the ones that we can do. Okay, now what else? Well, let's see. The derivative of the sine is the cosine. So up here I see the sine of x. Its derivative is the cosine. So its derivative is lurking about. So that will be another one that we can evaluate. Now what I might be tempted to do with the first one here is to say, well, because I'm taking the square root of something other than just x, I'm taking the square root of 1 minus x squared, maybe this is a good one for substitution. But think about the derivative of 1 minus x squared. It's negative 2x. There is no number that we can multiply negative 2x by to get x squared. Yes, we could multiply by negative x or the opposite of x, but that's not a constant. So it turns out that this one is not suitable for substitution. Okay, so we're going to rule that one out. Let's look around here. Here I've got another square root, don't I? Let's look at the stuff under the square root. Under the square root we have 1 plus the cotangent of x. The derivative of the cotangent is negative cosecant squared, and there's the cosecant squared. So I think that this one is another good one for our substitution problems. So among these last 2, we have to figure out which one is best for substitution. And I think this one's a little trickier to do. But the derivative, or the integral of x e to the x, there's not really anything that stands out to be substituted. You could think about the exponent, like over here, in the second one, the exponent has been changed from x to the sine of x. Well, here, the exponent is still just x. So substitution isn't really appropriate for this one. That's something that we would use in what's called integration by parts. Instead, it's going to be this last one that's good for substitution, the secant of 9t, tangent of 9t. I know a function whose derivative is the secant times the tangent. The argument of those 2 functions is 9t, whose derivative is just a constant. So those are the ones that work well. So let's look at the first one, this cosine of x e to the sine of x, and we'll do that one. That wasn't a very pretty e. There we go, e to the sine of x dx. As I indicated, the sine of x appears to be, or the derivative of the sine of x is the cosine of x. So let's do the substitution here. So I'm going to let u be equal to the sine of x. And then when we do the derivative, du is the derivative of the sine of x, which is the cosine of x, multiplied by dx. So over here, once again, I'll do a little bit of rearrangement. I'm going to have the integral. I'm going to have e, the sine of x we called u, so I'm going to put the sine of x up there. Dx we called, well, we're going to put the cosine of x together with the dx. And then when I make my substitution here, the e is going to be raised to the power u, and the cosine of x dx becomes du. We know a function whose derivative is e to the u. It's simply e to the u. And now we'll just resubstitute that u. Let's put the plus c there. When we resubstitute u will have e to the sine of x plus our constant. Okay, so let's do the others here. The next one on our list was 2y cubed, 1 plus 6y to the 4th to the 5th dy. So, as we mentioned before, the inside, its derivative is 24y cubed. I don't have the 24, but I do have the y cubed. So I'm going to let u be equal to that inside stuff. 1 plus 6y to the 4th. Then du is going to be simply 24y cubed dy. I don't have 24y cubed. I have 2y cubed. So I want to think about what I could do to 24y cubed to become 2. And if I multiply both sides by 1/12, 1/12 du is going to be 2y cubed dy. Again, if you want to rearrange things, we would have the integral of 1 plus 6y to the 4th raised to the 5th power. And then we group together the 2y cubed dy. And when we make our substitutions, we'll end up with the integral of u to the 5th, and then the 2y cubed dy becomes 1/12 of du. You can pull the 1/12 out front, integral of u to the 5th du. We use our formula for the powers. We have the 1/12. I say when I have u to a power, I have one more than that power, so u to the 6th, and I divide by my new exponent. And at the same time as simplifying, I'll get 1 over 72 here. I'll have u, which we said was 1 plus 6 to the 4th, 6y to the 4th. That'll be raised to the 6th power plus my constant. Next up, we have the integral of the cosecant squared of x times the square root of 1 plus the cotangent of x dx. The radicand, the stuff under the square root, is what will make u. U will be equal to 1 plus the cotangent of x, because the derivative of the cotangent is negative cosecant squared, but we'll fix that part. So du will be negative cosecant squared of x dx. If we multiply both sides by -1, it gets us that cosecant squared of x dx. Now, I'm not going to write all of the steps that I've been writing, but if I underline, the cosecant squared of x dx becomes negative du. So I'm going to put the negative out front. At the back end, I'll put the du. 1 plus the cotangent of x was my u, and so that's just going to be the square root of u. And of course, the square root of u we have to write as u to the 1/2, or think of it as u to the 1/2. I'll add 1 to that exponent, so I've got the negative that was already there. I'll add 1 to 1/2, which becomes 3/2, and then we have to divide by 3/2, which is the same as multiplying by 2/3. The way I like to look at that is when you take the derivative to check your work, I would bring the 3/2 down, multiply it by the 2/3, which would reduce to 1. Then we would add c, and if we rewrite it, we'll get negative 2/3 times the square root. U is to the 2/3 power, so I don't really want that square root anymore. So it's going to be 1 plus the cotangent of x raised to the 3/2 power plus c. And for our final integral of this collection, we want to do the secant of 9t, I believe it was, times the tangent of 9t dt. Again, I said it's helpful to say, hey, I know a function whose derivative is the secant of x times the tangent of x, and so what I'm going to do is I'm going to let u be equal to the 9t that's the argument. When I take the derivative of 9t is just 9, and so it'll be 9 dt. And here's the funny part. And we're going to find a sort of routine way to do this kind of a problem where the argument of our function, here 9t, is a linear function, something of the form mt plus b or mx plus b. But over here I have the 9 that's here. I don't have a 9 hanging out front, and so what I need to do is I need to multiply both sides by 1/9. So when we do our substitution, we'll have the 1/9 du back here. I'm not sure if I left enough space, but on the inside we'll have the secant of u tangent of u du. And I know a function whose derivative is the secant of u tangent of u. It is the secant. If that's a mystery to you, then you need to review your formulas. And u, we said, was the secant, or u, we said, was 9t. Okay, so for just a little bit later, here's the hint that I want to show you for this thing I call the linear arguments method. I wanted to find the antiderivative of all this business there. I wanted to find the antiderivative of this. Because I wanted to find the antiderivative, I automatically think, hey, there's the secant. What about the secant? Wouldn't that work? And if I think of it as the secant of 9t, when I take the derivative of that, I know I would multiply by 9 because of the chain rule. So to compensate for that product, we have to divide by 9 or multiply by 1/9. When we do definite integrals, we can actually bypass one of our steps by not resubstituting if we do something very carefully. So what we'll do is we'll do the ordinary steps for substitution, but instead of resubstituting, we'll make a change to the limits of integration so that they're in terms of u instead of in terms of x. So we'll do that with this first example here. All right, this one's kind of challenging, so we've got to be a little bit careful here. And it looks really awful because my integral goes from 0 to 1 over the cube root of 2, which is really kind of bizarre. But we'll figure out why it's so bizarre. Now, I am a new person to integration by substitution. I see the square root in the denominator, so I'm going to be tempted to say this, and this is not going to work for us. I'm tempted to say that u is equal to 1 minus x to the 6th. But when I do du, I get negative 6x to the 5th. And when I compare that with the power of x I have up here, I only have x squared. So that didn't work out for me. So I'm going to need to do something different. So let's erase this. So what I'm going to do is I'm going to think backwards, actually. I'm going to think about the x squared, and I think, hey, what do I take the derivative of to get something in terms of x squared? Well, I take the derivative of something involving x cubed to get the x squared. If I think about x to the 6th, x to the 6th is x cubed, but it's x cubed squared. Now that denominator then starts to look a little bit more familiar. I have the square root of 1 minus something squared, which reminds me of one of my inverse trig functions. So here we go. I'm going to rewrite this just slightly. I'm going to go from 0 to 1 over the cube root of 2. And then I've got x squared dx up top. And in the denominator, I've got the square root of 1 minus not x to the 6th, but x cubed squared, which is the same as x to the 6th. My substitution then is going to be u equals x cubed. Du will be 3x squared dx, which is perfect because I have that x squared lurking about up there. The problem is I don't have this 3, so I'm going to multiply both sides by 1/3. 1/3 du is x squared dx. Now, I'm going to do something a little bit odd here. I'm going to write this as x equals 0 to x equals 1 over the cube root of 2. X squared dx is going to be equal to 1/3 du in the numerator, and then in the denominator we have the square root of 1 minus x cubed. X cubed is now u, 1 minus u squared, which looks really familiar. Hey, that's the inverse sine's derivative. Now, what I want to do is I want to change my limits of integration. Originally, I said that x is equal to, x starts at 0. So if x is 0, I know that u is x cubed, which here would be 0 cubed, which is 0. So in the next step, I'm going to say the limits go from u equals 0. I don't really need the variable there, but I'm doing it for emphasis. And then I said we ended at the cube root of 2. So u is x cubed. That's why we had the cube root of 2. And it's not the cube root of 2. I'm sorry. It's 1 over the cube root of 2. We're going to cube that, which becomes 1/2. That's a little bit prettier. So we go to u to the 1, u equals 1/2. And we have du over the square root of 1 minus u squared, which becomes 1/3. Can't forget the 1/3 that's out there. Inverse sine of u evaluated from 0 to 1/2. We do not need to resubstitute because we've already made the substitution. The limits go from u equals 0 to u equals 1/2. Had we not resubstituted, they'd be going from x equals 0 to x equals 1 over the cube root of 2, and we'd have to resubstitute, but we don't have to do that. So this is going to be 1/3 inverse sine of 1/2 minus 1/3 of the inverse sine of 0. The inverse sine of 1/2 is pi over 6. And the inverse sine of 0 is 0. So this just ends up being pi over 18. For this next example, it's kind of a unique little example. And some people refer to what we're going to do as reverse substitution. Initially, I look at this and I say, hey, I'm going to be drawn to the stuff under the root, the x minus 1, and I'm going to think about letting u be equal to that. But the derivative of x minus 1 is just x, and I have this x squared lurking out front. Okay, that actually is going to be the appropriate substitution, but we're going to have to do something a little bit sneaky. So I'm going to let u be equal to x minus 1. du is just going to be the derivative of x minus 1, which is 1 times dx. So du and dx are exactly equal to each other. I'm also going to change my limits of integration like we did in the last example. When x is equal to 2, we're told that u is x minus 1, so it's going to be 2 minus 1, which is 1. And when x is equal to 5, u is 5 minus 1, which is 4. So my new limits of integration will go from 1 to 4. If I think about what I have the square root of x minus 1, which is now going to be the square root of u. I'll put that in. I'm going to be brave here. And dx, we said, was equal to du. So here's where things get a little bit funny. What's really nice about my substitution is that this expression, x minus 1, is really easy to solve for u, or to solve for x. If we add 1 to both sides, we get x is equal to u plus 1. So the x squared that we have out front, we can replace by the x by x plus 1, or u plus 1. So that's going to be u plus 1 squared. Now this is going to be, we're going to be able to integrate this, but it's going to be a little bit of extra work. We're going to have to do some algebra before we can do that. So the first thing I'm going to do is I'm going to expand out the x squared, or the u plus 1 squared. When I do that, we'll end up with the integral from 1 to 4 of u squared plus 2u plus 1. The u square root of u I'm going to write as u to the 1/2 du. And then I need to distribute the u to the 1/2 to all three terms in here. We're going to use properties of exponents and add the exponents. So we'll have the integral from 1 to 4. U squared is times u to the 1/2. That's 4 halves, and 1/2 will give me u to the 5 halves. Plus 2u to the 3 halves plus u to the 1/2 du. And now we use our formula for evaluating the integral of u to the n. We'll add 1 to the exponent, so my new exponent for the first one will be 7 halves. I need to divide by 7 halves or multiply by 2/7. Then I have plus 2 times, this is going to be u to the 5 halves. We have to multiply by 2/5 so that we get 1 when we differentiate. And then u to the 3 halves multiply by 2/3. Evaluate that from 1 to 4. When u is equal to 1, we're going to end up with, when u is equal to 4, we end up with 4 to the 7 halves plus 2 times 2/5, we could have written 4/5, I guess, times 4 to the 5 halves plus 2/3 of 4 to the 3 halves. And then we subtract. Now be careful here. When we're doing this, we have to subtract this entire business, which we have to put in parentheses. So it's 2/7 times 1 to the 7 halves, minus, we'll put the 2 and the 2/5 together to give us 4/5, 1 to the 5 halves, plus 2/3 times 1 to the 3 halves. And I've done the calculations for us. It turns out to be an answer of 6,904 over 105. The last thing I want to discuss is something that I call linear arguments. We mentioned this term before. An argument in this expression, the natural log of 4x plus the radical x, 4x plus radical x is called the argument of the logarithm function. This is a bunch of mumbo jumbo, but basically it says that if we know a formula for an integral, I can replace the x by a linear expression, and the formula carries on over, but we have to divide by basically the slope, which is essentially the derivative of the inside. This only works for linear arguments. It does not work for other expressions. And the reason it doesn't work for other expressions is because when you throw an x in and then try to check your work, it will probably require something like the product rule. So I'll show you how this works. We have the integral of cosine of 9x. Well, I know, and I'm just going to do a little guessing over here, I know that the derivative of the sine of 9x would be the cosine of 9x if I'm not a Smart Calculus 1 student. But I am a Smart Calculus 1 student, and as a Smart Calculus 1 student, I know I'd have to multiply by 9. So that means that the antiderivative of the cosine of 9x is not simply the sine of 9x, but what we're going to do is we're going to multiply essentially both sides of this equation by 1/9 so that we don't have to worry about that business. When we take the antiderivative, we're going to divide by the 9 that's in front there. So the antiderivative of this is just going to be 1/9 sine of 9x plus a constant. This is extraordinarily helpful as you go throughout and do some applications of these things. When we do things like integration by parts, it's really helpful to do that. Okay, so let's look at the next one, the integral of e to the 15x. Well, I would think that the derivative of e to the 15x would be e to the 15x. Oh yes, but I'd have to multiply by 15, so I'm going to compensate for multiplying by 15 by dividing by that 15. And we don't forget our constant. Let's do the last one first, actually, before we do the third one. 4x, radical 4x minus 9. Now I think about this as the integral of 4x minus 9 to the 1/2 dx. So I would think, oh, well, the antiderivative of this would be that same business to the 3/2 power. I'm going to multiply by 2/3 out in front to compensate for the exponent. But the inside isn't simply x, it is now 4x minus 9. Taking the derivative of this would require the chain rule, which would pop out an extra factor of 4. So we're going to multiply by 1/4 out front to compensate for that. So this would be, that'd be 1/6 of 4x minus 9 to the 3/2 plus c. For part C, I'm actually going to look at this and say, well, where do I see a linear expression? I see a linear expression in the 9x plus 7. So let's think about that if it weren't there. Let's think about it if it were just a simple x. I'd have 6 over x dx. Oh, that's antiderivative is 6 times the natural log of the absolute value of x. Remember, when we take the antiderivative of 1 over x, we want the absolute values to make the most general antiderivative we can come up with. So what I've done here is I've taken the x that's here and I've replaced it by 9x plus 7. So I'd have to replace this x by 9x plus 7. Let's do that. This is going to become 6, and I've left a little space, you'll see why in a moment, times the natural log of the absolute value of 9x plus 7 plus a constant. Again, if you think about the derivative of this, we would do 1 over the 9x plus 7. We would have to multiply by 9. So to compensate for that 9 that gets multiplied by, we need a 1/9 out in front. And so this reduces to 2/3 times the natural log of the absolute value of 9x plus 7 plus a constant. One last example to remind you of the applications of all this business. The reason we often start discussing integration is through areas. And so I'm asking, what's the area of the region bounded by y equals 1 over 2x minus 1 squared, which I've graphed for us here, the x-axis, and the lines x equals 1 and x equals 2. So I've got the green area as our region that's bounded. Integrals measure area. So I'm really looking for the integral from 1 to 2, and I'm going to rewrite this in a ready-to-integrate fashion. 2x minus 1 to the negative 2 power. I could use substitution. I have something raised to the negative 2 power, 2x minus 1, or I could use my new linear arguments method. Hey, 2x minus 1 is linear. Yay! Okay, so we take the antiderivative. When you take the antiderivative, you add 1 to the exponent, so that would be negative 2 plus 1 is positive 1. So we'd have to divide by negative 1. The inside we leave alone, 2x minus 1. And then in order to address the chain rule, we need a factor of 1/2 out front to compensate for the derivative of the inside. We want to evaluate this from 1 to 2. So those two numbers, those two fractions together multiply to give us negative 1/2. When we evaluate this at 2, I'm going to go ahead and write it in a more sensible form where we interpret the negative 1 exponent as 1 over that. So 1 over 2 times 2 minus 1 minus, and then we have negative 1/2 times 1 over 2 times 1 minus 1. And let's see what we get. This denominator, the first one, is going to be 1/3, but we've got a negative 1/2 out front, so it's minus 1/6. This other one is positive because I've got the two negatives here. The 1 over 2 times 1 minus 1 is 1, and then we multiply that by negative 1, or positive 1/2 essentially, so we get 1/2. So this is going to be 3/6 minus 1/6, which is 2/6, which is 2/6 I said, which is 1/3. So the area under this curve is 1/3. And let's see if that makes good sense. We started at 1, we ended at 2, so that's a width 1. And notice that we are within, now it doesn't look like a square, but it really is a square. We were within a square of dimensions 1 by 1, and so 1/3 seems like a reasonable answer in this particular case.